So our job now is really to try this out and to see if it's actually going to work. So we're going to try it out. Now in your notes you might want to leave a little bit of vertical space here like I have. And so to try it out, we're going to see whether or not we get back psi of x, so we don't know if we will, so this is a claim at this stage, as an integral dk, right, of some set of weights. So I'm going to put some square brackets here so I can write down what those weights are. But the idea is it's going to be some set of weights times then this factor of e to the ikx. And we had a particular guess for what these weights should actually be. We guessed this is what should be inside the bracket. Integral dx times psi of x times e to the minus ikx. Now what I want to do now is I'm going to show you mathematically how to manipulate integral expressions like this. And I want to go through this very slowly, step by step, the first time we're playing with this type of a manipulation, to give you some tips and pointers for your own ability to carry out such formal manipulations. And we will learn a number of mathematical lessons along the way, as well as testing out our key theory here. Very good. So the first thing mathematically I want to point out is that you have to always be very careful whenever you insert one integral expression into another. And one of the things you have to be very careful about is the meaning of your various variables. So for example, this x means where we are evaluating our wave function. And that x, if we think about our integral formula, is exactly the same x over here where we're asking for the value of psi. So that x and this x are actually the same thing. They mean the same thing. The x inside my square bracket, on the other hand, is something else entirely. Right? This x is actually summed over all possible values, right? It's an integral from minus infinity to infinity. Within the bracket, within the integral, x takes on all possible values, and I'm using it actually to add up these different numbers to finally get my weight that goes in the square bracket. So the way I like to think about it is I like to think about this x in here as like a temporary variable in a computer code where you're writing a function or a computer subroutine whose job it is to calculate this psi tilde of k. You're using this x inside here as some temporary variable that you're using to carry out this sum over all possible values. But once you're done computing the integral, once you're done, if you will, inside your function that returns this final value, which depends only on k, this x is gone. As soon as we leave the brackets, the scope of that temporary variable is over. So this x in here means something completely different from the x on the outside. So if we don't want to confuse ourselves whenever we make an insertion like this, we should be careful to make sure that any temporary variable names don't get confused with these external actual important variables. So the technical name for these internal variables are dummy variables or dummy indices of integration or dummy indices of summation. So that we don't confuse them, it's good to give them a different name, right? It's just a temporary variable, so instead of calling it x, I will call it x prime. So that's my first point on carrying out integrals like this. Now my next general mathematical point is that whenever you have a mathematical expression like this, and you're trying to prove something about it, and what you're trying to prove doesn't look, the integral that you have doesn't look at all yet like what you're trying to prove, your job is actually to massage this thing, right, and make different valid mathematical manipulations on it until you can get it to look like the expression that you're looking for. And as a little theoretical tip after many years, I can tell you that basically there are two main tricks we can use to massage an integral expression to get it to look like something else. The first of these tricks is integration by parts, because when you're doing integration by parts, of course, the derivative moves from one function to another function. It kind of changes the meaning and what's going on inside of your integral, and that's a great way to make some kind of progress as you massage your integral. Now this particular integral doesn't already have any derivatives in it. I could play some tricks and take some derivatives and put in some extra factors and take that route. But it doesn't look super promising. That's my first option. So I'm going to pass on the first option right now and think a little more, because I've got a second option for making progress on an integral, and that second option always is actually changing the order of the integration. So what I'm going to think about doing is actually changing the order of integrals. So I'm going to put a line above here, because this is just me thinking what I might do. I'm thinking maybe I'll write this as a dx prime integral first, and then a dk integral, right? And of course, just implicitly, we are, of course, integrating over all of the different possible valid values. Now, mathematically, if you think about what that really means, an integral is more or less just like a sum, right? So what I have here is I have a bunch of numbers that depend on x prime and k. So if I want, I could like make little dots to represent all of my different numbers inside that integral, all the different values of my integrand. And over here, I'm listing the various different values of x. And down this axis, or actually x prime is what I'm summing over. Down this axis, I'm listing all the different values of k. And of course, what this integral expression says is, okay, add up for a given value of k. While I'm doing this integral, k is fixed, I'm summing over all of x prime. So I'm basically summing everything in this row. And so first, I'm summing all of these rows, right? And I get the subtotal for each row. And then finally, when I integrate dk, I'm getting the grand total by summing my subtotals. Now, of course, all I've done is just added up all of these values on the inside. And by the commutative and associative properties of addition, of course, I can do that sum in any order that I prefer. So, for example, I could instead sum first the columns and get the column subtotals, and then sum all of those subtotals, and that's exactly what switching the order of integration would accomplish. Now, there is, though, because these are going to be infinite sums and these are infinite integrals, there is one mathematical technicality that we have to watch out for. And that is that you guys may recall when I have an infinite sum, under some conditions, I can get any answer that I want by simply switching my order of how I sum up the terms. So technically speaking, to ensure that that doesn't happen, what you want is, you might be familiar about this fact from infinite series. So in infinite series, the way you can make sure you have a good infinite series that's safe, that will always give you the same answer, is if it's what's called an absolutely convergent infinite series. So we just want to be a little bit mindful of that we want to make sure that we have a properly valid mathematical function. But generally speaking, except in relatively rare cases, we actually can just, without much thought, just switch the order of integration. Now, we will know, actually, if we've run into a problem, because if we switch the order of integrals and then start getting different types of answers, well, then we know that there was a problem. Okay, now, so I'm going to go on with this idea. I'm going to switch my order of integration. The next little tip I have with switching the order of integration is I want you to take a look at my integrand now. Right? You will notice that it has different factors in it. And some of these factors will be independent of my integral, right? When I switch the integrals, I'm integrating dk. And what you will notice is the first factor here does not depend on k. So as far as this k integral is concerned, my first term, the psi of x prime, is a constant, and so it can be pulled out of the integral. So my thought is I'm going to switch the order of integration, and when I'm doing my dk integral, I'm going to pull this psi of x out of that integral. Okay, so let's rewrite my integral now. So I'm now taking what is literally equal to this integral, right? So this integral, whether or not it's going to be psi of x, I don't know. But what I know for sure is I can integrate it. I can always switch my order of integration. So I've done that. I can pull out that psi of x prime. So I will write that. I can then integrate over all possible values of k. And now, while I'm at it, I may as well tidy up my integral a little bit. I have these two factors that depend on k. I might as well combine them into a single exponential. I notice both of them have a common factor of k, so I'll write this as e to the minus ik. And then I've got x prime from this term. This term is a plus ikx, but I can get that with a double minus sign, minus x, like so. So now I've transformed my integral. So just a couple of math lessons on this that I'd like to memorialize, because we can use it again and again when we deal with these Fourier type integrals. The first thing is that we can always, almost always, I guess I'll put a little quote around that, and we'll almost always, right, switch the order of integration at will. Right? And then what we want to do is switch it around into ways that are convenient for us, that get us towards the goal that we're heading toward. And in this case, our goal was just make some progress, so we've definitely changed things around here a little bit. The other thing is we can also move the factors within the integral past the integrals at will. At will, so whatever suits your fancy, gets things looking like towards the final expression that you're heading toward. But this is as long as they stay to the right of their integral, or the integral over their variable of their integral. Right? So where you might run into trouble is, it would be silly if I took this psi of x prime all the way over here past the dx prime. That wouldn't make any sense, right? Likewise, these factors with k's in them can't be moved past the k integral, because k is being summed over within that integral. Okay, so we've made some progress here, actually a lot of progress, because now psi of x it's getting closer to just being a psi of x, but we've now introduced this new quantity. So I've got some new mysterious function here. Whatever this thing is, right, once I integrate over k, it's going to be some mysterious function, so I'll call it m, and it depends on this difference, x prime minus x. So our job now is to figure out what this mystery function is, and then once we have it, we have to figure out how to integrate it against psi of x prime, and then we will see whether or not we can recover our psi of x. Now, this integral, right, I just happen to know what it is, so I do want to make the math work out just a little bit more neatly. There'll be less crossing out here on the screen. This is just an arbitrary mystery function anyway, so I'm going to define this expression actually as 2 pi times my mystery function. Okay, but it doesn't change the line of argument at all. It's just this will help us pick out what that function actually is. Okay, so then the question is, right, what we want to know is, what is that function? What is this function m of u, right? And I've defined it now, as you can see, to be 1 over 2 pi times this integral. So 1 over 2 pi times my integral minus infinity to infinity dk, right, of e to the minus ik, and I noted that this only depended on x prime minus x. So as you can see, I'm letting u actually equal x prime minus x. So it's really m of u is e to the minus ik times u. Now, let's consider this integral. So this is a second set of mathematical lessons we need to think about. So, well, when you begin to look at this integral, and think about it, you begin to realize we're running into a little bit of trouble here. So if I were to plot versus u, my e to the minus iku, of course that's a complex number, it's a little hard to plot, but we all know this is made out of sines and cosines. So let's imagine I had sine. Let's look at the sine part. The same thing happens with the cosine part. So if I plotted sine of ku, it would look something like this, right? It'd be a nice sine function. And now we have to imagine integrating this out to u goes to infinity. Now, when I do that integral, I find a little bit of a problem, right? When I integrate over this first hump, I get some answer. That's the value of my hump if I integrate up to that point. If I go a little bit further, you'll notice I'll get the minus of the first hump. My integral is going to be 0. Then it's going to become the hump value again, and then it's going to be 0. So I keep getting this alternating series of values as I take my upper limit of my integral out to infinity, but it's not converging to anything. It just keeps changing. Right? So I actually violated the one mathematical condition that actually allows me to switch the order of integrals. I have actually a term here which is not what's called absolutely convergent. It just keeps oscillating. Its magnitude isn't decreasing. So to get around this, we're now going to introduce an important physicist trick. And this is something called an integrating factor, or a convergence factor. So I'm going to multiply my function, right, by something. And the point of this, thinking like a physicist, is I'm going to do something to my function here that will not change any physical results that I calculate, right? It's going to change the math just a little bit, but it won't change the physical results, which is the key thing I care about. But what it will do for the math is to make everything nice and happy and properly well-defined. So that convergent factor then I'm going to use is e to the minus some very small number epsilon times the absolute value of k. So this is called a convergence factor. And my thinking on this, let's draw you a little sketch of what we believe this thing would look like. So here is e to the minus epsilon times the magnitude of k along my k-axis. Now this function, you will notice, when k equals 0, I get e to the 0, so its value is just 1. And if epsilon is a very tiny number, right, even for large values of k, if epsilon's super tiny, I still have essentially e to the minus 0. So it's going to be decaying, but very, very slowly. So I'm trying to sketch out a very slowly, that didn't look slow enough, very slowly exponentially decaying function. You know, something like this. And in fact, I'm going to choose that epsilon so small that if I think about this scale here, which I will call k max, over the range of plus or minus k max, there's essentially no difference from 1, which would not change my integral. So what I want to do is make sure this epsilon is so small, right, that there's no change in this function, even out to k max. And by k max here, I mean, again, one of these quantities like the maximum possible momentum in this universe, right? Our universe is finite. It has a finite amount of energy associated with it. If I use all that energy and use it to juice up my particle, there's still some maximum momentum my particle could have. So all of the physical action that we would ever see would all be occurring in this range of k, right? That's the only range of k that matters to our physical calculations, and so therefore this factor has essentially the value 1 everywhere, and I've not changed the physical answers that I can expect from this integral with this convergence factor. Now, mathematically though, it makes things nice and well defined, and we just have to remember that at the end of the day, we will have to take the limit that this epsilon goes to 0 and just make sure it doesn't affect any of our physical results. Okay, very good. So now that it's defined and now that it's a well-defined integral, our job is just to carry out the integral. Now we could go to Wolfram alpha, but I'd like to always have us do these things ourselves. These are always good practice. So let's carry out our integral. So this will equal then 1 over 2 pi times then, the way to do such an integral is to break it up into 2 pieces. So I will, because I've got that absolute value in there, so I will integrate over the positive values of k, e to the minus I ku, and then I have e to the minus, now if k is positive, absolute value of k just equals k, so this is e to the minus epsilon k. And then I have a second piece, which is where k will vary from minus infinity up to 0. These are the negative values of k. And again, I have e to the minus I ku. And my convergence factor now is e to the minus epsilon times the absolute value of k. But if k is negative, absolute value of k equals minus k. So this is actually plus epsilon k. So I now have those 2 integrals to contend with. And the next step on this is going to be to actually carry out now these integrals. They are standard exponential integrals, and we know how to carry those out.